This video provides a quick introduction to the concept of Maxwell relations. In our survey of thermodynamics until now, we have been encountering a variety of state functions that have very clear meanings. Those have been the internal energy, enthalpy, entropy, Gibbs energy, and Helmholtz energy. In addition to those, we actually have parameters, which are also state functions, that are easier to control in the laboratory: temperature, pressure, and volume. Well, the Maxwell relations show relationships between these state functions that are not obviously apparent. And they share some traits, right? So it turns out that each one of these 5 state functions of interest can be put as a function of something that are called natural variables, which are simply the variables that provide a thermodynamic equation for the state variable that is very easy and compact. For example, in the prior video, we have seen what the fundamental equation is for the internal energy. We have seen that combining the first and the second law, you can come up with an expression that looks like this. This is the fundamental equation for the internal energy, and entropy and volume would be the natural variables of that thermodynamic state function, which is the internal energy. So let me repeat a little bit the nomenclature again. Each one of these state functions is going to have a fundamental thermodynamic equation, which is simply the relationship of that function with something that we call natural variables. And the natural variables are the variables that provide a very simple thermodynamic equation for a given state function, right? So again, taking the case of internal energy, which is something that we have worked out in the prior video, we see that for the internal energy, which is our state function, we have natural variables, the entropy and the volume, that provide a thermodynamic equation, okay, for that state function, which is very simple, right? So you simply here have the dependence of the internal energy with entropy is just the temperature, and then with the volume would be the minus pressure. Okay, so this is going to be the case for also for enthalpy, Gibbs energy, Helmholtz energy, and so forth. There will be a fundamental thermodynamic equation for each one of those, and each one of those will have natural variables, and we will see how those look like in turn. Now, those won't be still the Maxwell relations. The Maxwell relations exploit another fact of a state function. Okay, so if you have, we know that the state functions are called exact differentials, and the definition of an exact differential for a function f that has natural variables x and y, for this function to have an exact differential, what happens is that the second derivative of that function with respect to the variables x and y, okay, does not depend on the order of the differentiation, okay, y and x. Okay, this is a condition that each exact differential has to satisfy, and state functions are exact differentials, and this is something that we know. Ray turns out for state functions, the path that is irrelevant, right? You can first change this variable, then change that one, and then the change to the function will be exactly the same one if you change first this variable and change that one to get, as long as the initial and the final points are the same, right? So that beautiful property of state functions, right, that they're path independent, that the only thing that matters is the initial step and the final step, not how you go through between those, okay, is going to allow us to work at these Maxwell relations using the fundamental equations for each thermodynamic variable. Okay, so in the next videos we're going to see those Maxwell relations using the fundamental thermodynamic equations for internal energy, the enthalpy, the Gibbs energy, and the Helmholtz energy.